right? And so before we had an impulse, and now we want a step. And it's going to be a unit, so it's going to go to 1, just like before. Let's get a straight line. And so we have a response that sits along the bottom, sits at 0. At t equals 0, our response comes up, and then it goes over to the right. And we're going to have a response of 1 at t equals 0. Right? And so we're going to call this phi. So phi, and then this is our Greek letter phi, capital phi. And so this is our unit step response, right? So a step function, and it's a common loading solution, and represented for like you drop a load into a truck, right? You don't have a load, you drop the load, and then the load is there. So it's not going to come and go. So the Laplace transform for a unit step function is our Laplace of capital phi of t. We have square brackets around our Laplace, is equal to our integral from 0 to infinity e to the negative st dt, which is equal to e to the negative infinity over s plus e to the negative 0 over s equals 1 over s. Should the first term be negative? Negative e to the negative infinity. Yes, correct. Thank you. What are the integral terms again? The 0 to infinity? Yeah. So this is is this one on our sheet? Number 30, with the A assumption. But this also lines up with number 3 from our Laplace transform sheet. So this is number 3 on Laplace sheet.
Professor, what's the difference between 3 and 30? Is it just like a time shift?
So yeah, 30's got a time shift in it. And I don't think we're going to do that in this chapter. Actually, I know we're not doing it in this chapter. So, so for the number 3, we're just interested, for this one, we're just interested in number 3, right, which is 1 over s. So that would be expected as phi is used to represent a step function, i.e., a step function with a displacement of 1. So as we consider linear systems in this class, we can scale the magnitude of the response of the amplitude of the impulse after the transformation is performed, right? So we can do our transformation and then we can do our scaling later. And that's what allows us to use it for everything. So I think the best way to kind of walk this, to show how this works is to just walk through an example. So let's look at the undamped case first. So the undamped case for a step response. So let's say, for a spring mass system subjected to a step response, assume 0 or assume no initial conditions. Right, that seems fair as we are I'm really interested in what the step response does to the system. So our equation of motion, right, is going to be mx double dot plus kx of t is equal to capital phi. Oh, that's a messy one. Probably. Let's do that. mx double dot of t plus kx of t is equal to phi of t. Right, so we can take the Laplace transform of both of these sides. So what's the Laplace of mx double dot? But, well, it's our whole Laplace term, right? But we're ignoring our initial conditions. So we're only going to be left with our, so for x double dot is s squared x of s, and then we're going to keep the m. So we have m s squared x of s. Yeah, so what about that minus xs naught? Do we care about that?
Would that go because we don't have any?
Yeah, we don't have any initial conditions, right? So let's just, we can write it. We've been writing it, but maybe we'll just drop it this time. That work? So we'll drop those, and then we have plus, do we have a damping term? No. And so what's the Laplace of just x? XS, right? And we drop our, well, there's no initial conditions with that anyways, right? So plus k x of s, and then the Laplace of phi, 1 over s. Right? And so step 2, what's step 2 in our 3-step plan? Yeah, that's pretty simple, right? Pull an excess out of each side, multiply it through, so I've got excess is equal to 1 over s. You can leave it separated, but we have an s, so we're not going to be able to pull that out through the Laplace. So let's just go ahead and combine those, I guess. Let's just go 1 over s times ms squared plus k. Right, and so is that going to show up on our Laplace sheet?
No, but I think you can rearrange it.
Yeah, so, well, I mean, just let's take a step back before, yeah, we need to rearrange it, like Lawson said. So what is not, like if you just look at that, how do you know that doesn't show up on our Laplace sheet? Yeah, so we don't have the Laplace in terms of k and m, we have them in terms of omega. So we need to pull out our mass, so it's easy enough to pull out of the first term. If we pull it out of the second term, we can do that by just leaving behind an omega. So we're going to get x of s is equal to 1 over m. I'm going to pull that out completely on its own, times 1 over s times s squared plus omega n squared. That makes sense to everyone? Right? Omega is the square root of k over m. So that's how you can see how that k and that m kind of end up with omega squared. So our 1 over m will pass through our Laplace transformation. What about what's on the right-hand side? Is that on our Laplace sheet?
Yeah, I'm pretty sure it is. Yeah, it's 1 over omega squared, 1 minus cosine omega t.
Perfect. Yeah, what number is it? Just 9. Okay, so number 9.
So then it's just that value times 1 over m.
Yes. Yeah, sorry, I was preparing for another question, and then that question came, and I was like, oh, okay, that's not what he's asking. So x of t, is equal to 1 over m, and then what we get for our Laplace, right? Times 1 over omega n squared times 1 minus cosine of omega n t. Brackets on the cosine, bigger bracket. So m times omega n squared, right? What does that give us? So we have a square root, and then all of a sudden you can break that out to just 1 over k.
You left it as m and omega n, would that be okay too?
Perfect.
Okay.
There's a simple, I mean, there's a simpler way to write it, but it's not going to change the answer, right? You know, if I was doing it in code, I might leave it that way, depending on how you defined your parameters. But it does break down into 1 over k. 1 minus cosine of omega nt. Pretty cool, right? So this gives us a solution for a step response. If you plot this out, and we'll look at a cleaner figure later, you're going to get something that looks like this. Which is a little weird because up until this point, we've always kind of started with things that oscillate around 0. But now we're going to oscillate around a value which is f naught over k. Right? So f naught is our, whatever the forcing function multiplied by our step function is. And so why does it oscillate around a center line there and not around 0? Oh no, did I just lose the other screen now? I'm just going to stop. Okay.
I think it's on a different channel.
Yeah, I think it is, and it's fine. I'll bug them after class. So, but is this working okay? I'm sure some necks are being strained, but yeah. So it oscillates not around 0 because we have a forcing function, right? So we have an offset applied to it. So let's do that same thing for a undamped mass spring. So for a undamped mass spring, you know, there's a remote here. Should we try to fix it? What's the worst that can happen? I'm real hesitant to, I don't want to, you know what, it's working. It could be worse, right? It could be worse. Okay, so for an undamped mass spring system, it's going to be the same, right? But now we're just kind of looking for a term that's going to pull energy out of the system. Oh, sorry. Yeah, I was underdamped. How about that? Does that make more sense? So we want the same thing, but we want to be able to pull energy out of the system, right? So our equation of motion is going to look a little bit different, right? We're going to add our damping terms. We have mx double dot of t plus Cx dot of t. There's an error in the notes. There should be a t there in number 33. Plus kx of t is equal to phi, capital Phi of t. Right, so we're going to add damping to this. Again, our first step is to take it into, to take the Laplace of both sides. Did you have a question? Okay. Good?
Oh, yeah.
Okay, so the first task here is to take the Laplace of both sides. So we can do that and then convert into the standard form. So actually, first, let's just convert into the standard form. X double dot of t is going to divide everything by whatever leads our x double dot term. So c over m becomes 2 zeta omega n x dot of t. That also needs a t. Plus omega n squared x of t equals 1 over m times capital Phi of t. Now can we, okay, now we can take the Laplace of it. We could have done it before. You just end up with a slightly different equation. I mean, it still works, but let's do it this way. So again, we're going to ignore our initial conditions. I can also, let me see. Is that a little, would you rather it be bigger and I slide more or smaller?
Bigger.
Bigger?
Yeah.
Okay. There's going to be more up and down movement here, but okay, so let's go and take the Laplace of both sides. And again, we're going to ignore our initial conditions. It just saves us a lot of writing instead of just writing them down and dropping them off. So we're going to have s squared x of s plus 2 zeta omega n. We have an s capital X of s plus omega n squared x of s is equal to 1 over m, right? Times what? 1 over s. So it's the same as before. So our next step, once we're in the S space, what's our next step?
So isolate XS.
Yeah, isolate x of s and solve for it. So we have an x of s in each term. We can go ahead and pull that out. X of s is equal to, let's just go ahead and write it. S squared plus 2 zeta omega n s capital S, oh, definitely not that, plus omega n squared is equal to 1 over m times 1 over s. And now, oh, sorry, that is multiplied. Now we can divide that, multiply both sides by 1 over s squared plus 2 zeta omega n s plus omega n squared, and we end up with s of x is equal to 1 over that whole term, s squared plus 2 zeta omega n s plus omega n squared equals 1 over m times 1 over s. Yeah, thank you. Too much copying. Okay, so is this something that we can get in that table? That 1 over s is kind of confusing, hanging out on the end. Yeah, part of it, except you also have that 1 over s.
Can we just multiply by the plus? Because that's just 1.
You have to do something else in the plot space. So what we can do, though, is just multiply the right-hand side of the equation. So let's just multiply the whole equation by 1, right? And that 1 in this case is going to be omega n squared over omega n squared. Does that make sense? At least seeing conceptually what I'm doing. So this results in x of s is equal to 1 over m omega n squared times omega n squared over s squared plus 2 zeta omega n s plus omega n squared. So does that look like something we have exactly in that form? Yeah, number 11, right? So, I mean, there's other ways to do it. Don't get me wrong. Like, this isn't the only mathematical way to do it. It just gives us a nice, clean equation on the outside.
BS wouldn't treated them as 2 separate plus. Like, it has to be one entire function. Aside from the n.
So when you take your inverse Laplace, right, you want it to be one function. But, I mean, there's things you can do. But for this example, like, this is a cleaner way to do it. You know, kind of like the general math thing. There's always more ways. It just depends how much time you want to spend. Igor?
Instead of multiplying by omega n squared over omega n squared, you just multiply by k over k, and you just do expression of k over n to get the same omega n squared on top. Just simplify it. You're gonna end up with a k anyway. Just simply straight.
So we want things in omega for our Laplace table. That's the answer I'd give you on that one. Because I don't, like, we'd have to resolve our Laplace transforms in terms of another parameter. Does that make sense? I mean, at least in sense of like the boundaries we're operating on, which is Austin spent a whole weekend once typing up 31 Laplace transforms. Doesn't want to do anymore. So if you find errors in them, let me know. But I think I've got most of them. So yeah. So let's go ahead and take the Laplace of this. So the component here that leads does not have any s's in it, right? So we can just pull that through. Does that make sense? And then number 11 is going to give us 1 minus omega over omega d e to the negative zeta omega nt sine of omega d. So let's go ahead and write that out. So we have a taking the inverse Laplace transform. We're going to end up with x of t is equal to our leading term there, 1 over m omega n squared times 1 minus omega n over omega d e to the negative zeta omega nt sine of omega d t plus phi. Right, and so this is for there's an error in equation 38. It's an underdamped case, right? So for zeta, oh, wrong. So for zeta is less than 1. So let's take a look then at what these plot out like. Right, so our undamped case is our blue line. And so we're going to start down at 0 where our step is applied, and then we're going to come up and down and kind of cycle forever, right? We never have any energy dissipated from the system, so it's kind of this imaginary system that just vibrates forever. And then our underdamped case is our orange dashed line. And that's going to come up and isolate and eventually settle around a new amplitude, which makes sense, right? You drop a weight in the back of a truck, the truck springs compress, it might vibrate for a little bit, but then it settles around its new amplitude. And then our amplitude is a function of the force applied divided by the stiffness of the reacting system.